When the power goes out after a storm, your refrigerator becomes a countdown. The freezer still looks safe, the door still seals, and the food still feels cold for a while. But that calm look is exactly what makes the problem dangerous. Nothing looks broken yet. Even though every hour after the outlet goes dead, heat is already working its way back inside. That is the moment a solar heated absorption cold chest becomes interesting. Not as a shiny replacement for the refrigerator in your kitchen, but as a second cold source for the times when the grid is down, the cabin is off power, the RV is sitting in the sun, or the garage freezer suddenly has no compressor to lean on. This is not about making your kitchen look futuristic. It is about having another path to cold when the normal one stops helping. Before you build that path, the first move is to measure the appliance you already own. Put a plug in watt meter between the wall outlet and your refrigerator or freezer. Then leave it there long enough to catch real life. The compressor cycling the door opening, warm groceries going in, and the freezer recovering after dinner. The source claim says a refrigerator can cost around $200 a year to run, but in a real house that number should be treated as a starting question, not a fact. Your fridge may be better, it may be worse, and your electricity rate or daily habits may change the math completely. The meter gives you the first honest number, and that number tells you what kind of project this is. If the load is high, the idea has a savings angle. If the load is low, it may still have a resilience angle, especially if outages are part of your life. For some homes, this will not be the first project worth building, and that is fine. But if you have ever opened a freezer after a long outage and wondered whether the food inside is still safe, you already understand the pressure. A refrigerator is easy to ignore until the outlet stops helping. This system only makes sense when it is placed in the right category. It is a heat-driven absorption cold chest, not a normal solar panel fridge with a battery and inverter and a small electric compressor. That battery-powered version can work, but this idea is different because sunlight is used as heat first. That heat drives a sealed absorption cooling unit, the kind found in many camper and RV refrigerators. Inside that sealed unit, heat starts the cycle. Ammonia moves through the system. Heat is rejected out the back, and the cold side pulls heat out of the storage space. The strange part is that sunlight, which normally makes a garage or shed harder to cool, becomes the push that helps protect cold. A kitchen fridge needs electricity because its compressor needs electricity, but cold storage only cares about one thing: whether heat is being removed faster than it leaks back in. That is the opening that makes this system worth looking at. It gives a homeowner another way to think about refrigeration, especially in places where grid power is not guaranteed. The important boundary is simple. The sealed ammonia water cooling unit is not the part you build from scratch. It is not something to cut open, refill, weld, or modify because a diagram looked easy. The real build happens around the sealed unit, the heat source, the insulated chest, the airflow behind the coils, the level the sensor location, and the way the result is proven. That still leaves plenty of project to work with. The useful version starts with a rated donor absorption unit and turns it into a second cold storage layer for a cabin and RV, a farm shed, a backup food chest, or an outage setup. If the grid goes down, the question is no longer whether your kitchen refrigerator is modern. The question is whether you have another way to keep heat out of the food. The first physical object in this build is not the solar collector. It is the donor absorption unit, because if that part does not already work, the rest of the project has nothing solid to stand on. A used camper absorption refrigerator may show up in local listings for around $150 to $250, but that number depends on your area, and it should never be the only reason you buy. The working donor matters more than the cheap donor. Look at the back before you imagine the finished build, and check for a readable label, intact tubing, solid brackets, and no obvious damage to the cooling unit. If the back looks crushed, stained heavily rusted, or abused, that is not the right starting point. An ammonia smell is also a serious warning sign. If the seller cannot show that the unit cools in its original setup, that is another reason to leave it alone. A donor unit has to prove the basic cooling cycle before sunlight becomes part of the story. The donor should be tested first in the way it was designed to run. Let the cold plate inside start doing its job. Let the rear coils get warm, and let the unit prove that it can move heat before you ask it to run from a different heat source. The two signs you want are simple cold, where cold belongs, and heat leaving where heat belongs. That second sign matters because the rear side of the unit is where unwanted heat escapes. If that heat is trapped in a sealed corner, the cold side gets weaker and the project starts fighting itself. This is why camper refrigerators have vent paths, and why the back of the unit cannot be boxed in like spare storage. Level also matters. The source claim says a tilt beyond 3 degrees can stall the cycle, so the exact number should be checked against the unit you use, but the principle is still important. A crooked absorption unit can look finished and still cool badly, which is why a bubble level and a few shims can matter more than another expensive part. Stand behind the donor unit, and the idea becomes easier to follow. A compressor refrigerator uses electricity to squeeze and move refrigerant, while an absorption refrigerator uses heat to drive a different loop. Heat enters at the generator section, where it separates the working fluid inside the sealed system, and from there, ammonia vapor moves through the tubing, while part of the system rejects heat out the back. That rear section is the warm side, and it has to breathe for the cold side to work. Inside the storage space, the evaporator pulls heat out of the chest, which is why the food gets colder. Nothing mystical is being created. Heat is simply being moved from one place to another. The basic chain is straightforward once you see it physically. Heat goes in at the generator, heat leaves out, the rear, heat is pulled from the storage space, and the fluid returns so the cycle can repeat. This is the reason the idea is tempting, because if heat can drive the loop, sunlight can become more than a problem on the roof. In the right setup, solar heat can become the push that protects a cold chest during the part of the day when the sun is available. The important phrase is in the right setup, because a propane flame, an electric heating element, and a solar heat loop do not deliver heat in the same way. They recover differently, overshoot differently, and fail differently. That is why the build cannot be judged by one warm pipe or one cold metal plate. The real question is whether the storage space stays cold when the collector heat loop absorption unit insulation and test load all have to work together. The build has to answer 3 practical questions. Can the solar side deliver enough heat? Can the absorption unit turn that heat into cooling? And can the insulated chest hold that cold long enough to matter? If one answer is no, the whole story gets weaker, but at least the test tells you where the weakness lives. That is the useful part of building it honestly. The system does not need a perfect claim. It needs a test that shows what is actually happening. This is the part that decides whether the solar version is a real cold storage system or just a good-looking experiment. Moving heat from a collector to an absorption generator is not automatically simple, because the generator section does not just need something warm nearby. It needs enough useful heat delivered into the right area at the right time without opening or damaging the sealed cooling unit. A standard flat plate water collector may be useful for hot water, warm storage, or a low temperature experiment, but it is probably the weak path for a freezer claim. The absorption generator in a camper-style unit is normally driven by a concentrated heat source, such as a burner or a purpose-built electric heater. A loop of ordinary warm water touching the outside of the tube may look clever, but contact alone does not guarantee that the fluid inside is reaching the temperature it needs. That is why the collector choice matters. If the goal is only to test whether solar heat can help a cold chest during the day, a lower temperature solar loop may still teach you something. But if the goal is freezer-like performance, the heat source has to move into a more serious category. Evacuated tube, solar thermal, concentrated solar thermal, high temperature heat transfer fluid, or a hybrid setup that keeps the donor unit's rated heat source available when solar heat is not enough. This does not make the project less interesting. It makes the target clearer. The easy version is a solar-assisted cold chest. The hard version is a solar-driven freezer, and those are not the same build. Layout still matters. In many real homes, the collector wants to be on a roof, a rack, or an open sunny patch outside, while the cold chest wants to sit in shade. That layout may need a small DC circulation pump, a controller, and a temperature sensor that moves fluid only when the collector is actually hot enough to help. A tiny pump is not a failure of the system. It simply admits that your house is not a perfect diagram. The pump only helps if it moves heat at the right time. If it runs too early, it can move lukewarm fluid and waste the useful window. If it runs when the collector is truly hot, it gives the generator a fighting chance. The bad version is simple, in the wrong way. Collector in the sun pipe, running to the donor unit. No control, no sensor, and no proof at the generator. The uncomfortable part of this build is the heat exchanger. You are trying to warm the generator section from the outside without cutting the sealed cooling unit and without guessing at the heat input. That may mean a clamped-on high-contact sleeve, a wrapped contact exchanger, or another removable method that keeps the sealed tube intact, but the contact method is not magic by itself. Heat still has to cross the interface. Too little heat and the unit starves. Too much heat and the system can behave badly. The safer framing is this: the sealed cooling unit stays intact, the external heat system stays controlled, and the test measures whether useful heat is actually reaching the generator. That is the difference between a risky hack and a system worth testing. The real question is not whether the collector feels hot. The real question is whether the generator is receiving enough controlled heat to make the absorption cycle do real work. A good heat loop can still lose to a weak storage space, and that is the part many builds underestimate. The collector may be hot, the pump may be moving fluid, and the donor unit may be cooling. But if the insulated chest leaks heat too quickly, the result can look exciting in the afternoon and disappointing by evening. This is why the test should be built around something physical, not just a pretty sensor reading. An old chest freezer shell can be useful if it is solid, because it already has thick walls, a lid, and a gasket. Run your hand around the seal and look for places where warm garage air can sneak in, especially at the corners, the hinge side, and the spot where a sensor wire might pass under the lid. If the rubber is cracked, flattened, or pulling away, that problem should be fixed before the cooling unit gets any credit. Now give the camera something real to watch. Set a jug of water in the middle of the storage space. Add a freezer pack beside it, if that is how you plan to use the chest during an outage, and place the temperature sensor near the load instead of against the cold plate on the wall. A jug of water is harder to fool than a metal surface because it changes temperature slowly and behaves more like the thing you are actually trying to protect. This is the visual test the video needs. The garage is warm. The collector is outside the pump comes on when the sun is doing real work, and the rear coils are shedding heat while the lid stays closed. Inside the water jug and freezer pack become the job the system has to do. The graph still matters, but the shot is the cold mass sitting in the middle. If the sensor is touching the evaporator, you are measuring the machine's best surface, not the storage job. If the sensor is sitting with the load, you are measuring whether this setup can protect food instead of merely making one piece of metal cold. That difference changes the whole video. A cold plate is a demonstration, but a chilled load in the center of the chest is evidence. The audience does not need to love charts to understand that picture. Now the system has to survive the part that makes solar cold storage difficult sunset. A solar heated absorption chest can look impressive while the collector is hot, but that is the easy test. The harder test begins when the sun drops, the garage stays warm, and the food still needs protection. The source claim says a single stage system can hold around 30 degrees Fahrenheit, and that number should be used as a target to test, not a guarantee. If the center load holds near that range during the useful sun window, the project has earned attention. If it only touches that number for a short moment, you have a good clip, not a dependable backup. The bigger headline number is 0 degrees Fahrenheit, because that is the freezer target people want to hear. But 0 is not the same promise as 30. 30 degrees shows that the system can become a serious cold chest. 0 degrees asks for a different level of heat delivery, insulation, storage mass, and proof. If the heat source is only an ordinary flat plate water loop, the honest answer is that you are probably not building a real freezer yet. You may be building a solar-assisted cold chest, which can still be useful during an outage, but that is not the same as holding a freezer load at 0 degrees. Chasing 0 means a stronger rated unit, a staged design, a high-temperature solar thermal source, a hybrid rated heat source, or some combination that proves the result with the sensor sitting in the load. That distinction actually makes the video stronger. It turns the headline into a challenge instead of a trick. The first gate is useful cold storage. The hard target is freezer performance. The night problem also has to be designed in from the start. The system needs some kind of buffer, which may be cold mass inside the chest, like water jugs or freezer packs, a thermal storage tank on the heat side, or the donor unit's rated backup heat source, for the hours when solar heat disappears. If none of those exist, sunset is not a minor detail. It is the failure point. This is where the visual payoff belongs. Open the lid after the sun has dropped, not at noon, when the system is showing off, and show the jug the freezer pack and the sensor reading from the center of the load. If the chest is still holding useful cold while the outlet is doing nothing, the idea has weight. If the number climbs too fast, the test still gives you something valuable. It tells you where to look. Collector temperature generator, contact, pump timing, insulation, heat, rejection, storage mass, or backup heat. That is not a failed video. That is the build, telling you what kind of cold system you actually have. This system belongs where backup cold matters: cabins, RVs, farm sheds, garage freezers, outdoor utility spaces, storm-prone homes, and rural properties where an outage can last longer than the food in the freezer wants it to. For most homes, the kitchen refrigerator stays on the outlet because it is convenient, familiar, warranted, and easy to replace. The modern compressor fridge won the kitchen because it fits the kitchen, and there is nothing weak about admitting that. The solar heated absorption chest is not competing for the cleanest spot beside your cabinets. It is competing for the job your kitchen fridge is worst at, which is staying useful when the outlet stops being dependable. That is the useful shift, because it turns this from a miracle appliance story into a backup cold storage system with a specific place to win. This also explains why the technology became niche without needing a conspiracy. A compressor fridge has a retail aisle, a warranty path, technicians a normal plug, and a shape that fits the way American houses are built and serviced. A solar absorption cold chest asks more from the site and more from the homeowner. It makes you ask where the sun sits, where the heat goes, and whether the pump moves fluid at the right time. Then you check the boring things that decide the result. The unit sits level. The rear side can breathe, and the center load still holds cold after sunset. That is harder to sell in a store, but harder to sell does not mean useless. It means the homeowner has to treat it like a system, not a product. Start by measuring your current fridge or freezer for a week so you know what load you are trying to replace, support, or protect. Then test the donor absorption unit with the temperature sensor sitting beside a real load, such as a water jug or freezer pack, instead of chasing the prettiest reading on the coldest surface. After that, the use case becomes clearer. It may be bill savings, cabin cold, RV backup, farm shed storage, a storm outage layer, or no project at all. That last answer is allowed because a good measurement can save you from building the wrong thing. But if your property does need a second cold source, this is where the idea gets powerful. Sunlight does not have to stay on the roof, and with the right heat source, the right donor unit, the right insulated chest, and the right sunset test, it can be put to work protecting cold when the outlet stops helping. Measure the load, build the heat system honestly, and make the cold mass prove it.